you are watching this video, you're probably getting ready for your AP Precalculus Unit 2 Progress Check A exam that your teacher is forcing you to take on AP Classroom. This video will help you get ready for it. It covers pretty much everything. I create my own problems that are going to be like what you would see on this test. Hopefully it gets you good and prepared. Now, this is me just going over a bunch of problems. I'm not reteaching anything. I'm not explaining a ton how to do stuff. If you need to see that, watch some of my reteaching videos. They're there. Watch them. Please like, subscribe, all that good stuff. Let's get right into it. Again, these are the types of problems you should expect to see on the Progress Check 2A exam found on AP Classroom. Not exactly the same, but close. Given an arithmetic sequence with a common difference of 3, find the 10th term if the first term is 7. Now, first thing that we have to do is we have to write down the equation for an arithmetic sequence. So the equation for an arithmetic sequence is going to be A sub n equals the first term plus n minus 1 times d. Now, A sub n stands for the nth term. A sub 1 stands for the first term. N has to do with whatever term you're talking about. Minus 1 is minus 1, and d is the common difference. Let's label what we know. It already told us that the common difference is 3, which means to get from one number to the next, one number to the next, one number to the next, we subtract 3 every time. I need to find the 10th term, which means that's going to be my n. And the first term is 7, so that's going to be my A sub 1. So we just literally plug stuff in. So A sub 10 is going to equal A sub 1, which is 7, plus n minus 1, which is 10 minus 1, times d, which is 3. And now it's a good old PEMDAS problem. 7 plus 9 times 3 is going to be 7 plus 27, which is 34. Fun. In a geometric sequence, if the fourth term is 81 and the common ratio is 3, find the first term. Well, let's write out our geometric sequence formula, shall we? We've got A sub n is going to equal A sub 1 times the common ratio to the n minus 1 power. Now let's label what we know. We know that the fourth term is 81. Okay, so you would be like my n, and you would be like my A sub n. My common ratio is r. Find the first term. Okay, so it looks like I'm working a little bit backwards here, but that's okay. I can handle this. I'm a math teacher. A sub n is 81. That's going to equal the first term, which is, I don't know, times r, which is 3, to the n, which is 4, minus 1 power. Okay, 81 is going to equal A sub 1 times 3 to the third power. 3 to the third power is 27. So I've got 81 equals A sub 1, the first term, times 27. Divide both sides by 27. It looks to me that that first term is 3. Not so bad. Not so bad. I can handle that. The first 3 terms of a sequence are 0.5, 0.76, and 1.125. I know what I did. I know that that's a typo. That should be 0.75. I don't know why I did that. Silly me. All right. Now that I fixed it, I apologize. That's supposed to be what I have. I'm going to turn those into fractions just for funsies. You're a half. You are 3/4. You are 9/8. Now I know that this isn't arithmetic because this would have me add a quarter every time, and I didn't add a quarter to get from this guy to that guy. So it's not arithmetic, so it's got to be geometric. So I have to ask myself, what am I multiplying every time to get from this guy to the next? Well, I'm going from 1 to 3 to 9. So that part of my common ratio is going to be I'm multiplying the numerator by 3. The denominator goes from 2 to 4 to 8, and I'm multiplying that guy by 2. So my common ratio is 1.5 or 3 halves, however you want to view it. Okay, so I'm going to write out the same exact formula that I had. I'm not going to write it out. I'm just going to reuse it. So my common ratio is that. My first term is that. I care about the sixth term, so you're going to be my n. And now I just kind of plug things in. And that's what I want to do. I want to find the sixth term. So I want to find a sub 6 is going to equal my first term, which is a half, times the common ratio, which is 3 halves, to the n minus 1, which is going to be 6 minus 1 power. I'm just going to turn it into 5 to give myself some space. Okay? All right. Oh, boy, this is going to be tough. 1 half is 1 half. 3 times 3 is 9. Times 3 is 27. Times 3 is 81. Times 3 is 243. 2 times 2 times 2 is 8. Times 2 is 16. Times 2 is 32. Half of that is going to be my sixth term, and that's going to be 243 over 64. Not pleasant. Not pleasant at all. I didn't like it. Too many fractions. Just like the world today. Too many fractions. Because of war. What is the end behavior of g of x? Ooh, okay. G of x is it's an exponential function. It's growth. And it's shifted over to the left 1. Okay, but it doesn't move up or down. So basically what I'm looking at is something that looks like this. It is an exponential growth problem. By the way, that is what determines that it's growth. The fact that it's greater than 1 and not in between 0 and 1 makes it growth. There's no number in front of it spinning it upside down. If there was a negative in front of it spinning it upside down, that would make it upside down, but we don't have that. And since I'm not adding or subtracting anything out here, I basically have a regular old standard looking exponential growth problem. So the end behavior has me flattening out right at 0. So the limit as x approaches negative infinity of g of x is going to equal 0. As I move to the right, as my limit increases, or as x increases, g of x becomes infinity because it's now moving upward. And that is a typical exponential growth looking model. Okay, so that shouldn't be too much of a shock for anybody. Now I have to rewrite f of x to a base of 2. F of x to a base of 2. All right, right now my base for f of x is 1/8. Ooh, but you know what I could do? I'm going to do this one step at a time. Okay, I can turn 1/8 into 1/2 to the third. Now, that is not a base of 2 yet. That is a base of a half. So if I want to make that 2 and move that to the numerator, if I have it in the denominator already, moving it to the numerator is just going to have me moving it up and making the exponent negative. So 1/8 is the same as 2 to the negative third. So let me fix that. Let me write this out. F of x, that's supposed to be an f, is going to equal not 1/8, but 2 to the negative third power to the 2x power. Now, when I have a parentheses with an exponent taken to a power, you multiply the exponents. Remember algebra 1? So I'm going to multiply these two, and that gives me a final result of f of x equals 2 to the negative 6x. And there you have it. Rewrite g of x so that the exponent is no longer a sum. Okay, well, g of x looks like this, and the exponent is a sum. So we have to work our way backwards. We have to think, what must have happened to get something where I have 4 to the 1 plus x power? Well, what must have happened that you are adding exponents? When you multiply terms of the same base, so if I have something like a to the nth, or second, times a to the third, I add those exponents. Okay, so 2 plus 3. Now what I have is not a, what I have is 4. So what could I, thinking my way backwards, if I have 4 to the 1 plus x power, in order for me to add exponents, it must be because I multiplied the same base in the first place. So 4 to the first power times 4 to the x power would give me 1 plus x if I only kept the 4. So I can rewrite this out as g of x equals 4 to the first power, I don't need to say anything, times 4 to the x power. Don't need that invisible 1. Okay? Now I need to solve f equals g. I need to set these two guys equal to each other. Well, before I do that, well, let's just set it up. Let's just completely set it up, okay? I want to try to be cute, but it's really easy for me to do, and I don't want to be too cute right now and just, give away some of the fun. 1 over 8 to the 2x is f. That's going to equal 4 to the 1 plus x. Now, what I need to do is I want to come up with some kind of equation so that I can make it look like this. Now, why would I want to make it have the same exact base? Well, if I have the same exact base, like 2, for example, whatever my exponent is going to equal my exponent, and I could just say n equals m. So if I can only make these the same exact base, I can make that work. Well, 4 and 8 should be doable. I mean, doable. Silly me, punning so hard. I already know that this could be rewritten as that. So this could become 2 to the negative 6x. I can turn 4 into 2 to the second power, and then I have an exponent of 1 plus x. Now, when I do that, I'm going to multiply these two exponents together. That requires distributive property. Be careful. But what I have is 2 to the negative 6x, the left side didn't change, is going to equal 2 to the 2 plus 2x power. Now that I have the same exact base, I could use this property right here and just say negative 6 is going to equal 2 plus 2x. Negative 6x is going to equal 2 plus 2x. Oh boy, would that change things. Okay? Subtract 2x. Subtract 2x. Negative 6x equals 2. Divide by 2. Divide by negative 8. Divide by negative 8. Cross you out. X equals negative 1/4. Listen, I never said it would be pretty. I just said it would be fun. Hi, negative 4. How are you? I'm doing great. Thanks for asking. By the way, I'm at work right now, so if you hear random children screaming in the hallways, I teach in Norristown. I mean, not Norristown. Somewhere else. Describe the graph of f of x plus 2. There's f of x. So let's just ignore the plus 2 part. We'll get there. Okay, this is what I have so far. I have something in the form of f of x equals a times b to the x. That is an exponential function. In this case right here, okay, my a is negative. So that's going to count for something. I'll get there in a second. It's also -2. That's going to count for something. My b is in between 0 and 1. So the first thing that I need to focus on is that guy right there. My b being in between 0 and 1 makes it decay. Okay, Donkey Kong. Now, decay looks like this, generally speaking. However, since I'm multiplying my decay by a negative number, it flips it upside down. So it no longer looks like this. It looks like this. Now, by multiplying it by 2, it kind of skinnies it a little bit. So it makes it steeper. I know that picture probably didn't do it justice, but that's what happens. By adding 2, now, all of a sudden, now I'm doing that. I'm shifting it up 2. So let me get rid of this whole mess. Okay. It is going to look like a reflected exponential decay model. I guess we'll say, since that is a horizontal shift right there, we'll say it's like compressed. And shifted up 2 units. Now, I'm going to simplify h of g of x. So here's h, here's g of x. Are you serious? Can you not see the sign? All right, I had to take a step away. Remember how I said I teach when someone knocked on my door, despite the fact that I have a sign? You know who you are. I'm not going to say your name, but if you're watching this, you know who you are. She shares the name of a famous musician who sings like this. Where was I? Simplify h of g of x. So here's h, which looks like it is some type of area-looking formula, like maybe a cylinder along those lines-ish, but not really. And I have to plug in g of x. So remember, h of g of x means you're going to start out with that outside function, and then you're going to plug in that function. So I'm going to start out with h. And every x that I run into, I'm going to put a big fat parentheses around it. So pi, big fat parentheses, squared. Now, g of x, I'm going to call red, looks like u. So I'm going to have 2 big square root x minus 1. Okay. Now, to simplify this, pi still lives on the outside. I have 2 times the square root to the second power. So 2 to the second power, that part becomes 4. The square root to the second power cancels itself out. That part becomes regular old x minus 1. And now I have a distributed property problem. So let me just quick rope those two together. 4 pi times x minus 1. Distributed property is going to be 4 pi x minus 4 pi. I feel like I did this a bunch of times in the last problem, but I'm doing it again. Rewrite f of x with a base of 2. Right now, the base is a half. So all I have to do here is just take that 1/2 and say, you want a base of 2, huh? Well, let's pretend you're 1 over 2 to the invisible 1, and then move it up and make it a negative exponent. Boom! So 1/2 is the same as 2 to the negative first. So f of x is going to equal negative 2 times 2 to the negative first to the x power. Whenever I have something with an exponent taken to an exponent, you multiply exponents. And so finally, f of x is going to equal negative 2 times parentheses 2 to the negative x. I did it. Find the inverse of h. Okay, but I only care about the inverse being, we'll deal with that in a second. I have to first find the inverse of h. So let me do that. Let me do that right above my head. Okay, so this is regular h. In order to find the inverse of an equation, I'm like to call u y. So I'll rewrite u quickly as y equals pi x squared. The first step into finding the inverse is swap your x and your y. So now it's going to be x equals pi y squared. Solve for the new y. So the first thing I'm going to do is divide both sides by pi. Divide both sides by pi. That's going to cross out. Gross. Now I have pi over, or x over pi equals y squared. Let me move that y squared to the left so it looks prettier and also so I can shift things a little bit. In order to get y all by itself, I have to square root everything. You probably heard that scream. So that cancels out. Whenever I square root both sides, I must attach the positive or negative to the right side. So what this leaves me with is y equals positive or negative square root of x over pi gross. Now the last thing that we're going to do is, I'm not going to call it y. I'm going to call it h inverse. So h inverse of x equals positive or negative x over pi. Not pleasant. They want me to find 3. So if I take 3 and plug it in, okay, h inverse of 3 is going to be positive or negative square root of 3 over pi. Now they're saying, I only want my answer to be positive, so let's just keep the positive answer. Instead of positive or negative root 3 over pi, I just want the positive root 3 over pi, and that's my answer. So the reason why I threw in that little wrinkle is you never know if someone's going to ask you to make it just the positive version only, because we know that if we take the inverse of what was given to us as a parabola, it's going to end up looking sideways, which is no longer a function. So I added that little wrinkle. Just like this place is adding more little wrinkles to me because I'm a teacher and not Norristown. Norristown's great, by the way. I do like it. It's crazy, but I like it. All right. Find f. So we got a bunch of composites here. Okay, so you should be a little O. But we've got a composite, a couple of them. So f of g of negative 2 means the first thing I need to do is find g of negative 2. So here's negative 2. So g of negative 2 is going to be negative 3. So g of negative 2 is going to be negative 3. Cool, got it. Now that I knew that or know that, I have to find g or f of negative 3. And here's negative 3. F of negative 3 is 11. Now I need to find g of f of 3. So let's first find out what f of 3 is. Here's x, so f of 3 is negative 1. So g of f of 3 is negative 1. So g of negative 1 means I go to negative 1, and g of negative 1 is 0. Composites. This is just plain gross. Now I'm going to rewrite this as 2 times f of g of negative 1 plus 4g of 0 minus 1. G of negative 1, what is it? G of negative 1 is 0. Oh. 2 times f of 0 plus 4. What's g of 0? G of 0 is 1. So 4 times 1 minus 1. Let's scooch all that stuff over here. 2 times f of 0 means 2 times 5 because x is 0. So 2 times 5. 2 times f of 0 means 2 times 5 plus 4 minus 1. 10 plus 4 minus 1 is going to be 13. And there you have it. G inverse of f of 2. Well, let's find out what f of 2 is. Here's 2. F of 2 is 1. So I need to find the G inverse of 1. Now, what you're doing with the G inverse, what you're supposed to find is you kind of reverse the order in which you do things, right? If I said, hey, find out what G of 3 is, you would say G of 3 is negative 8. So if I were to say, let's flip that around and find out the inverse of negative 8, you go in reverse order now. Okay, so if I were to say the G inverse of negative 8, you start out with G, and then you get that 3 value, you go in reverse. So similarly, G inverse of negative 1 means I go in reverse. A regular one, I go in reverse. So I go to G, I go to where regular 1 is, and I get 0. Which means if I do G of 0, I get 1, and this is just the inverse, which means the reverse way of doing things, because the inverse is just a reflection over the x equals y axis. You know this. Gross. All right. Let's move my face again. F of x is red. G of x is blue, just like roses and violets. What am I doing? Find G of f of 5. All right, well, let's find f of 5 first. Here's 5. So f of 5 means I go along the red line, and f of 5 is going to be 1. So f of 5 is 1. So now that I know that, I can find out what G of 1 is. G is the blue guy. So G of 1 means I go to 1 all along the blue guy, and it lives right there at 2. So G of 1 is 2. So you plug it into the one guy to get the other guy. Okay? Now, just like in the last problem, when I'm asking you to find the inverse, I go in reverse order. Now, I will show you graphically why this is going to make sense, but let's just do the problem first. F of negative 1 means the F inverse of 4. So I take F, which is red. I find out where my answer is 4. So here's 4 right here, and that seems to happen at 8. Now, see, I really can't draw it out. What you would do, though, is if you could draw it out, you would have something that looks like this, and that's just not going to look right. This is not going to look right. I'm not going to be able to make it work now with the picture that I have. I think I can make it work with these guys, though. Describe 3 g of x. Well, g of x is what looks to be some kind of logarithmic function-looking thing right there. Okay, that's what g of x appears to be. Now, when I multiply something by 3 to it, it scrunches itself in. Okay, so it's going to be the same graph, but compressed. Wow. So it might look something like this. See, I'm not even going to try. I'm not even going to try. Describe G inverse, which is going to be this. Now, okay, this is one I do want to graph. Now, remember, the inverse of an equation graphically is when you take the line y equals x. So I'm going to draw the line y equals x. I'm going to draw it through here. And what you do is you actually reflect this line over that axis. So it's going to look something like this. So what it appears to be is it appears to be the right side of a positive quadratic. That's what it looks like to me. Okay, you draw yourself a line across y equals x, and then you reflect it. So whatever happens on the left, which appears like it's curling around, you curl it around, and since that kind of like shoots to the right, you shoot that up. We're finally at the calculator problems. Where can I move my head so that it's not in the way? How about you? How about right there? Let's do it. All right. The graph on the right shows the value of an investment account. So what do we have? We have time in years, value in money. So at the very beginning, I start out with $1,000. After 2 years, I have $1,102. Write a linear equation, L of x, for this data. So a linear equation requires linear regression on my calculator. Let's scooch to the side and let's see how that's done. All right, linear equation. I can handle this. Even though I really don't need a calculator for it, I'm just going to do it anyway. Stat. Edit. I have 2.0 1,000, so let me put those points in at a time to keep things consistent. That is a 0 and not a 1. 1, 0, 0, 0. Okay. My other point is 2 and 11 hundo and 2.50, so 11 hundo and 2.50. Man, am I so cool? I really am. I really am not. All right, so those are my 2 points. I have to find a linear equation, so I'm going to go to stat, I'm going to go to calc, and I'm going to do lin reg, which is the fourth option there. So I don't need to store this. I'm looking ahead. It looks like I don't need to use this equation later on, so I'm just going to go straight to calculate. And there you have it. Y equals 51.25x plus 1,000. Or in this case, L of x equals 51.25x plus 1,000. All right, so the equation that I came up with, I'm going to call it L of x is going to be 51.25x plus 1,000. Probably don't really need a calculator for that, but you know what? I used it, so sue me. Now what I'm going to do is I'm going to use the same exact data, the same exact table that I typed into my calculator, and I'm going to find the exponential function. I'm going to call that e of x. All right, so we're now going to use the same exact data to find an exponential function. So we're going to call that e of x. I already have my points in, so I'm just going to go straight to calc. I'm going to go to exponential regression, which I believe is 0. Yep. So exponential is 0. It looks like in part C, I'm going to use this equation. So I'm going to store my equation in y equals. So I'm going to do that by going to store regression equation, hit vars, go to y vars, and type out my function y sub 1. And this will save my equation in y sub 1 whenever I graph it later on or whatever it is that I need to do. Calculate. And that is a lovely, lovely, lovely equation. We will write this out as e of x equals 1,000 times 1.05 to the x power. Okay, that guy ended up being e of x equals 1,000, makes sense, times parentheses 1.05 to the x power. And again, why did I say that makes sense? Because at 0, I'm at 1,000, which means if I were to plug in 0, this whole thing would become 1, so I get 1,000. Okay? Use the equation in B to estimate the value of the count after 5 years. So I'm just going to run to my calculator and plug in 5 for x and see what I get. Now, C here is asking me to use that equation that I just found right there to estimate the value of the account after 5 years. So since I stored this equation, if I hit y equals, now, by the way, that is 1,000. I don't know why TI-84 decides to do this. 99, whatever. If I hit graph, I'm not going to see anything, but that's okay because all I have to do is find the value at 5 years. So if I hit second, trace, and type in my value of 5, enter, it gives me the number that I need. So the number that I need, and keep in mind we're dealing with money, so all these decimals are kind of not super necessary. The amount of money that my account is worth after 5 years is $1,276.28. Now, since we're dealing with money here, I'm going to make sure that I round it appropriately. So I have $1,276. and 28 cents. You can't forget that 28 cents. Very important. Okay, 50 Cent would agree with me. I mean, you just add 32 more cents and then you get him. 50 Cent's a rapper if you don't know who he is. Check him out. It's a really weird problem. We're going to let d of x equals L of x minus e of x. So I'm actually going to type into my calculator u minus u and let my calculator find the maximum value of d. And if you're wondering, what real life application is this? There really isn't any. But this is just me using my calculator to see if I remember how to find the maximum value of something. So let's see how it's done. Okay, so part D here is kind of strange. It's asking me to take the linear equation that I got and subtract out the exponential function that I got and then graph that to find the maximum value of D. A very bizarre pre-calculus question. So I'm going to get rid of that guy because I really don't need it. I will need it, but it's already out of order, so why bother? 51.25x plus 1,000. And I'm going to subtract out my entire exponential function. So let me use parentheses because I'm always very paranoid. 1,000 parentheses 1.05 close parentheses to the x, hit right, close parentheses one more time. So this is my linear equation minus the exponential function that I just got. Let's hit graph and see what I get. Can't see it. Oh, I actually can see it. I'm very surprised at that. I was expecting to not be able to see it, but I see it just fine. My job is to find the maximum value of D, which is what we're calling this brand new equation. So if I want to find the maximum value, which appears to live right around there, I'm going to hit second calc, go to maximum, which is 4. And my maximum lives there, so I have to make sure that my left bound is somewhere to the left of it, which it kind of already is right there. Move to the right. My right bound is going to be to the right of my maximum. So my maximum lives in between these two bounds. Hit enter. And the maximum value of D appears to be the point 1.00. Is that 60 or 00? I think that's 60. Or is that 00? Oh, gosh, my eyes are so bad. It is 10 because it's right there. 1.008. So we'll call it 1.008. I'm writing it out on paper. And then the y value is going to be 1.2500. So 1.25. I can handle that. Not bad. All right, so this gave me the point 1.008, or at least I thought it was 1.008, and then 1.25 after things round out nicely. Okay, so a little bit of exponential regression, a little bit of linear regression, a little bit of maximums, a little bit of plugging stuff in. Fun. Okay, let's keep going. Let's keep this train rolling. This dinosaur train. Let's just keep it rolling. Gross. All right, so now we're talking about a rabbit population. Starts with 50 rabbits at year 0. The population then follows an exponential growth model. Use exponential regression to find an equation for the data. So I'm going to throw that into my calculator. I'm going to do exponential regression and see what happens. All right, so we've got this problem about rabbits and stuff, and it wants us to make an exponential regression to find an equation for the data. So let's plug the data in. Stat, edit. Just be careful with the typos, although the left side should be easy to handle. 0 through 6, like so. And then we've got 50, and then we've got 75, 112, 168, 252, 378, 567. I don't think I made any typos there. Let's go with it. All right, so now I need to find an exponential regression model. So I'm going to quit out of this. I'm going to go to stat. I'm going to go to calc, and my exponential regression is at 0. So you can scroll down and hit enter, or you can just hit 0. I did both. It looks like that I'm going to use this equation later on. So what I'm going to do is I'm going to store my regression equation so that when I hit y equals, it's there. Did this before. So I'm going to go to vars, I'm going to go to y vars, I'm going to go to function, and I'm going to hit y sub 1. Okay? So when I calculate, I get that gross-looking equation right there. But that's my equation for the data. It's awfully close to 50, but I'm not going to use 50 because, Precalculus says I'm not allowed. And that's awfully close to 1.5, but I'm not allowed to use 1.5 because, again, Precalculus. But I'm going to write out my equation in a second. So what happens is I get the equation y equals 49.96 times 1.499 to the x power. So almost 50, almost 1.5, but the numbers slightly changed just to add a little bit of variance, stuff like that. Predict the rabbit population at year 10. So I'm going to plug in 10 to that guy and see what I get. So in order for me to predict the rabbit population at year 10, I already have my equation plugged in right there. So if I hit second table and go to 10, there's my guy. I could also have hit second trace and typed in 10, but I'm going with this because it's just a different view from what I did before. I have 2,858.13. You know what? I can't have 0.13 rabbits. That's unethical. So I'm just going to say 2,858 rabbits. 2,858. Wow, rabbits are really fast at populating. I wonder if that's like a thing. I don't know. After how many years should you expect the population to be 10,000? Now, what that looks like is I want this to be 1,000, 10,000 equals 49.96 times that. So I am solving here. Now, I don't know logs yet. So what I'm going to do is I'm going to have that guy still in my equation, and I'm going to set another y equals at 10,000, and I'm going to find out where those lines intersect in my graphing calculator. Now, after how many years should you expect the population to be 10,000? Well, what that means is I'm going to have my y equals 10,000. So I'm going to do this a little differently. I'm going to set this equal to 10,000 and solve this by seeing where my lines intersect. Now, let me graph both. I don't see that intersection, probably because 10,000 is a kind of a big number. So what I'm going to do is I'm going to change my window. And since I used y equals 10,000, why don't I take my y equals or my y max and make that 10,100? Just so I can definitely see it. Maybe I'll make it 11,000. Not that it's going to make too much of a difference, but it'll help. Now I see my one line. I don't see my other. So obviously I don't have my intersection yet. It's going to be somewhere over here. So why don't I turn my window to, I don't know, let's make the X max be 50, because why not? And now I see my intersection. So in order to find the intersection between these two lines, I hit second, trace, takes me to calc. I'm going to hit 5 for intersect. And whenever you're doing the intersection and you have both equations, all you have to do is hit enter, enter, enter. That's just a fun fact. And the intersection is going to exist at 13.0949, and y is going to be 10,000. We know that. So what this means is we're looking at year 13.095. So somewhere in January of the 13th year, but we'll just put 13.095. And it looks like our magic year is 13 years and a little bit after that. Years. So you start out with 50 and you end up with 10,000. Holy crap. Pardon my language. That's a lot of rabbits. That's a lot of rabbits. That's a lot of rabbits running around asking for fruity cereals. Those rabbits, don't they know tricks are not for them? They're for kids. By the way, Tricks, if you ever want to sponsor me, I'm right here. Last problem. In this table, we start with 1,000 grams of a radioactive material at time t equals 0. Now, this is one of those decay problems. When you have a radioactive material, after time, it gets smaller. The material follows an exponential decay model. Decay, Donkey Kong. Use exponential regression to calculate a model for the data. So I'm going to run to my calculator. I'm going to hit the whole stat edit thing. I'm going to type all that in, exponential reg, see what I get. So here we have another table of values, and I'm going to use exponential regression to create a model once again. So let's go to Stat, let's go to Edit, and put those values in. I'm going from 0 to 6, not to be confused with 0 to 60, and that's how I drive 1/4 mile at a time. Fast and Furious. I've got a perfect 100. Oh, like me. I've got 55.2. 31.8, 17.6, 9.7, 5.4, and 2.9. Don't make any mistakes. Easy to make typos on this. I want to use exponential regression. And it looks like I'm going to use this formula again. So I'm going to hit Quit, Stat, go to Calc. 0 is exponential regression. We should know that by now. And like I said, since I'm going to use this equation again, I'm going to store my regression equation into y sub 1. So I'm going to go there. I'm going to go to vars. I'm going to go to y vars, function y sub 1, and then we can calculate our baby. And there you have it. So it looks like we're looking at y equals 100.902 times 0.556 to the x power. So the equation that I got was y equals a little over 100, and then 0.555, but we rounded it to 556 to the x power. All right. So again, kind of makes sense. I'm going to have a little bit of variance because the numbers aren't exact. We will see why that's the case in problem C. But now what I have to do is I have to use this information to find the half-life. What is the half-life? The half-life is how long does it take for my material to be cut in half. So I care about what happens when my total amount is 50. So 50 is going to be equal to 100.90 times 0.556 to the x power. Again, just like in the last problem, I don't know nothing about logs. So I'm going to type this guy I'm going to leave that there in my calculator. In another y equals part, I'm going to set it equal to 50. And I'm going to see how long it takes to get my stuff to cut in half. Now that I have my equation, I'm going to use this model to find the half-life. Now, what does half-life mean? How much time it takes to cut this guy in half. We started out with 100 grams. So I care about what happens when my total amount is 50. So I'm going to go to y equals, and I'm going to make a second equation at 50. And I can find out where these guys intersect. Okay. Now, if I hit graph, I won't see that because 50 is way up here. I can't see it. So if I change my window and change my Y max to maybe like 60 or something like that, I should be able to see what I need to see. And there you is. So way up here is going to be my intersection. So whatever X value that is going to represent my half-life. So I'm going to find the intersection by doing second trace. I'm going to hit 5 for intersect. Whenever you're doing the intersection of two equations, you can just hit enter, 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 and for whatever reason, TI-84 is all good about that. And you get 1.195, which means 1.195 years. Now, that makes sense because after 1 year, we're at 55.2, so it shouldn't take much longer to go from 55.2 to 50. But that's our guy, 1.195. And it didn't take long at all, 1.195 years. Now, the reason why this makes sense is after 1 year, I went from 100 to 55, which is almost half. So it's not going to take too much longer to go from 55 to 50, only an additional, fifth of a year, give or take. Sketch a residual plot to show why the linear model blah is not suitable. Now, I know it's not suitable because it's exponential, but let's sketch the linear plot to find out why. Now, what I'm going to do here is I'm going to sketch a residual plot using that linear model that I see. So what I want to do is I want to clear out all of my y's. However, I'm going to leave my points exactly where they are. Now, what I need to do is I need to see these points on the coordinate plane. So I'm going to go to second, y equals takes me to stat plot. I'm going to turn my plot on and leave it at these dots right here. Now, since this is a statistical thing, I'm going to hit zoom and go to zoom stat, and I get to see my dots. Okay. Now, what I don't see is the linear model that I'm comparing this to. So let's go to y equals and graph that out. Negative 14x plus 80. When I graph that, I see my linear model compared to my dots that I have. I know it's hard to tell, but there's a blue dot right there. And I have a dot underneath and 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 a dot right above. And what we're looking at is if you tilt your head sideways just a little bit, like a curious little puppy dog, you're looking at your residual plot with dots above, below, lower, below, right around the same. It looks quadratic, even though we know it's not, but it looks quadratic when you were to draw this out on a residual plot. So we're going to use this picture right here to draw our residual plot. All right, so in order to sketch a residual plot, you're going to look at the stuff that you have on your calculator. You're going to look at the fact that you have a line that looks like this, and you have a bunch of dots that kind of go like this, and stuff like that happens. Okay, I know that's not exact. But what you do is you kind of tilt your head to the side and say, all right, it looks like I have a dot above, and then all of a sudden I have a dot below, and then I have a dot below, and then a dot below, and then a dot below, and then like maybe something like this happens. And you should be able to look at that and say, that follows a quadratic looking pattern. So since my residual plots, my residual points follow a pattern, the linear model is not appropriate. It's not good. And we know that already because we said it was exponential. But when you're looking at residual plots, what you're really looking for is, do you see some type of pattern, maybe some type of quadratic looking pattern? If you do, then it's not linear. What you hope to find is like if you're given a linear model and things seem to be scattered all over the place and there's really no pattern or something like that, that's when you would look at that and say, that is when a linear model is appropriate. Here, not appropriate. Not appropriate at all. So that is progress check 1, 2, 2B. This should help you feel a lot more comfortable for whatever AP classroom exam that you're going to take for AP Precalculus. So if you need a little extra help, go to my videos. I have one that's 1.1 to 1.4 reteaching, and I have another one that's 1.5 to 1.8 reteaching. Watch those. They're like 55 minutes each or 50 minutes each. Good stuff there. But this should kind of give you a good idea as to what you should expect on that AP Precalculus Unit 2 Progress Check A exam. Have fun. Good luck. Thanks for watching. Bye.